So before I get too involved in this, a couple of things that I want to remind you of before I get too in-depth into these derivatives and antiderivatives. I want to remind you the difference between an antiderivative and an indefinite integral. So an antiderivative is just the function. It's just whatever expression I want to find. And if I'm doing an indefinite integral, it takes the antiderivative and it adds in a constant at the end plus c. And that constant is called the constant of integration. Now, what that does is it makes it so that instead of having just one function, which is the antiderivative, the indefinite integral represents all functions that have that as their derivative. So let me go ahead and jump into this. These are common derivatives and antiderivatives that hopefully everyone will know by the end of this. So remember, if we take the derivative of any constant, any number by itself, we should always get 0. If I integrate any constant, any number by itself, we should get c times x plus my constant of integration. Now notice this is a lowercase c, and that is an uppercase c. So that's the big difference there. Make sure you differentiate between them because little c and big C could be two different numbers. That's important to keep in mind. Now I'm going to talk about the power rules. So the power rule with derivatives is we multiply, so we take this x to the n, and we multiply by the current exponent, so n. So we'll do n times x, and what we'll do is we'll drop the exponent down by 1, so x to the n minus 1. Now, when I do the antiderivative, when I integrate this, I do the exact opposite. So instead of taking the power, which is n, the exponent, and dropping it by 1, what I'm going to do is I'm going to kick it up by 1. I'm going to make it n plus 1 instead of just n. And instead of multiplying by the derivative, instead of multiplying by the exponent, I'm going to divide by the exponent, so I'm going to divide by n plus 1. Again, don't forget plus c, plus your constant of integration at the end. Now, for the next one, that is the natural base, that is e, which is approximately 2.718. We are taking that irrational number and raising it to the x power. Now, the reason, again, we keep this one separate from all the other cases is because it's special. When I take the derivative of e to the x, I get just e to the x. Same thing happens with the integral. Since its derivative is the same, the integral will be the same. All I'm going to do is add plus c, plus my constant of integration at the end. Things get a little bit different when I make b as my base. It could be any number, so I could, for instance, have 2 to the x, and I want to take the derivative of it. What I'll do is I'll multiply by the natural log of that base. So for instance, again, if it's 2 to the x, I'll write ln of 2, the natural logarithm of 2, and we multiply that by the b to the x, the base to the x. So again, if I were to do that with the 2 example, it'd be ln of 2 times 2 to the x. So when I take the integral, when I do the antiderivative of it, what we're going to get is, instead of multiplying by the natural logarithm of b, we're going to divide. So we're going to have 1 divided by ln of b, of that base, times the base to the x. And again, don't forget your constant of integration. On the next one, we have to take the derivative of the natural logarithm, which means what we are going to do is make it 1 over x, okay? And what else we are going to do is, again, that kind of corresponds to the other one, this one over here, is if I try to integrate this 1 over x. Now think about this. This is the integral of x to the negative 1 dx. You can't really add 1 to that exponent and get out something with an x because you get x to the 0, which is just a constant. So instead, again, it's reversing this derivative process. So when I take the derivative of 1 over x, we actually get back the natural logarithm of x plus c. Okay. The other one I'm going to mention is we do the logarithm with any base that we want. So what we can do is, again, kind of follow this. This one involved the chain rule up here, so I can kind of follow the same chain rule idea up here. So what we'll do is we'll do 1 over x, and we're going to put the natural log of b in the bottom. Now, there's no corresponding integral of this, so this is just a derivative formula. So that's an important thing to think about. The next thing I'm going to talk about is some trig functions. So we'll pay very close attention to some of those. So the derivative of sine of x is cosine of x, and the derivative of of cosine of x is negative sine x. And so we're going to pay very close attention as we take derivatives over here. So actually, I'm going to reverse those arrows. So notice this. In this case, my sign changes. So when I took the derivative of cosine, I got negative sine. So if I'm taking the integral of positive sine, I should get negative cosine x plus c. Now, in this case, when I took the derivative of sine, I got regular cosine, not negative. So if I take the integral of cosine, I should get just plain old regular sine. And remember, these are going to be important. You'll probably want to either memorize these or some way, shape, or form try to keep them in your head. Again, if you can remember one of them, if you can remember the derivatives, you can probably figure out these integrals pretty quickly. The derivative of tangent should be secant squared x. And if you take the derivative of cotangent, you get negative cosecant squared x. Again, kind of the same idea. So we're going to flip this around. So if I'm doing secant squared, I should get tangent x plus c, because again, derivatives and antiderivatives should be opposites of each other. But notice here, we had a negative cosecant squared. So if I have a positive cosecant squared that I'm integrating, I should get a negative cotangent of x plus c. So keep in mind, keep track of those signs there. For secant, we should get secant x times tangent x. And for cosecant, we get negative cosecant x times cotangent x. Notice again, reminder, all of these cos are the ones that have the sign changes. So that's another thing to keep in mind when we're doing this. Although it's kind of reversed in this case for the sine function is, our answer has a co in it. Our answer has a co in it. So that's what I was going to keep in mind there. For secant tangent, we should get back out the original function, which is secant x plus some constant. And if we do the negative cosecant cotangent, the positive cosecant cotangent, because that's positive, we should get the reverse, which is negative cosecant x plus c. So again, notice on these, we're looking at our answer having the co in it. So not the tangent, not the sine, not the secant, but these cos. Cosine, cotangent, cosecant. They're the ones that get the negatives, okay? So that's something to keep in mind there. We have some others down here, and these are just important ones to think about, is the inverse functions. So for instance, if I take the derivative of the inverse of sine x, we get 1 over the square root of 1 minus x squared. So kind of following the same logic, if I integrate that same 1 over the square root of 1 minus x squared, we should get the inverse sine of x plus c. Hopefully you guys also remember these are also written as arc sine, arc cosine, arc tangent, all of that. So following the same logic, inverse tangent's derivative is 1 over 1 plus x squared. It could also be written as 1 over x squared plus 1. So when I integrate that, I should get tan inverse of x plus c. And when I take the derivative of the inverse of secant, we get 1 over x times the square root of x squared minus 1. So if we integrate that, we should get inverse secant of x plus c. Some things to remember about these is, remember, the cos just have opposite signs. So like, for instance, if this were arc cosine instead, or inverse cosine, all I would do was make it negative. If this were inverse cotangent, I would just make this negative. If this were inverse cosecant, I would just make it negative. So again, when you do the cos, you just change the signs. The same thing would apply over there on the other side with the derivatives. Antiderivatives, the integrals. Hopefully this helps you guys fill in all of the important information that you need to have as far as derivatives and antiderivatives or integrals. And again, make sure you think about this little tidbit of information here about the difference between antiderivatives and indefinite integrals. Hopefully, again, this helps you guys better understand this stuff, or at least have all of them in one place.